Welcome to A2 System Software. An operating system doesn't just provide a user interface, it is the invisible manager juggling absolute chaos. Without these core mechanisms, your computer would crash the moment you opened a second application. In this unit, you will discover exactly how the OS allocates limited CPU time among competing processes, how it handles sudden hardware demands, and how it perfectly fakes having more memory than physically exists. This forms the theoretical backbone of your Paper 3 exam. The CPU executes instructions sequentially, meaning a single core processor can only run one process at a time. The scheduler decides who goes next. We will explore first come, first served, the simplest non-preemptive strategy where processes wait in a queue. We will trace shortest job first, which minimizes average waiting time, but requires impossible advanced knowledge. We will see how round robin uses time slices to prevent starvation and keep systems responsive, and we will evaluate priority scheduling, where critical tasks jump the queue, but low priority processes risk being ignored forever. But what happens when something unpredictable and urgent occurs, like a hardware failure or a division by zero? These are interrupts. You will learn to categorize hardware and software interrupt sources and manage their priorities. More importantly, you will trace the exact sequence the processor takes during the fetch-execute cycle to handle them, pausing the current process, saving the context to the stack, executing the interrupt service routine, and restoring the system as if nothing ever happened.
Next, we tackle memory management. Modern systems regularly run 15 gigabytes of applications on just 8 gigabytes of physical RAM. They do this using virtual memory, extending RAM onto secondary storage. You will learn how a technique called paging divides physical memory into frames and logical memory into pages. You will calculate page sizes and use page tables to translate logical addresses into physical ones, allowing non-contiguous allocation without crashing the system.
We will also explore segmentation, an alternative memory technique. Segmentation divides programs into variable-sized logical segments, reflecting the actual structure of your code and preventing memory access violations. But relying on secondary storage has a fatal flaw. You will analyze disk thrashing, the severe performance collapse that happens when a system spends more time swapping pages between RAM and disk than it does executing processes. You will learn exactly why this death spiral occurs and how the operating system responds. This unit takes you under the hood of modern computing. You will trace complex scheduling algorithms, map out interrupt handling step by step, and calculate memory addresses through page and segment tables. These are the exact tools Cambridge examiners test in advanced theory. Take your time, attempt the practice traces, and you will master it.